Welcome back, everyone. Ready for another deep dive?
Always ready to explore.
Excellent. Today, we're tackling a concept that's foundational to calculus: limits.
Limits. A gateway to understanding how functions truly behave.
Exactly. And to guide our exploration, we've got these notes titled Limit of a Function. Sounds a bit technical, I know.
No, it can seem that way at first, but trust me, the idea itself is pretty intuitive once we break it down.
Right, because ultimately it's about understanding what happens to a function as we get closer and closer to a certain value.
Precisely. And the beauty of limits is that they let us analyze what's going on even when we can't directly plug in that specific value.
Okay, I'm intrigued. So where do we even begin with this whole limit business?
Well, these notes kick things off with a question. Imagine we have a function, let's say xx plus 2.
Okay, xs plus 2. Got it.
Yeah.
Pretty standard function.
Right. Now the question is, what happens to this function as x gets closer and closer to the value 2?
Interesting. My first instinct is to just plug in 2 for x and see what we get.
That's a natural inclination, but with limits, we're not necessarily interested in the function's value at x equals 2.
Oh, okay, so we're not just evaluating the function at that point.
Not quite. We want to understand the function's behavior as x approaches 2. Think of it like zooming in on a map.
I like that analogy. As you zoom in, you start to see more detail, a clearer picture of what's happening in that specific area.
That's the idea. Instead of looking at the big picture, limits allow us to focus on a specific point and see how the function acts in its immediate vicinity.
So instead of plugging in 2 directly, how do we figure out what's happening as x gets closer and closer to 2?
One way is to test out values of x that are just a tiny bit smaller and a tiny bit larger than 2, like say 1.999 and 2.001.
Ah, I see. By getting really close to 2 from both sides, we can get a sense of where the function is heading.
Precisely. If the function's outputs for those nearby values are getting closer and closer to a specific number, then we can say that's the limit as x approaches 2.
It's like we're sneaking up on the function's target, seeing where it's aiming, even if it never quite hits the bullseye.
A perfect way to put it. And there's a special notation we use to express this mathematically. Lim xa fx equal L.
Whoa, hold on. Let's unpack that for a second. What does all that mean?
Sure thing. It looks more complicated than it is. Lim just stands for limit. Xa means as x approaches the value a, fx is our function, and L represents the limit itself, the value the function is approaching.
Okay, so in our example with x plus 2, a would be 2, fx is the whole function itself, and L is the mystery value we're trying to find.
Exactly. It's all about understanding how the pieces fit together.
This is pretty cool. But is it always this straightforward? Are there situations where finding a limit gets trickier?
Absolutely. Sometimes a function might act differently depending on whether x is approaching our target value from the left or the right.
Wait, so the direction we're coming from can change things?
Yep. Think of it like driving towards a landmark. You can
Mhm.
approach it from different streets, maybe even different towns.
I see. So even if the destinations is the same, the journey can influence how we get there.
Precisely. We call these one-sided limits. They describe the function's behavior as x approaches our target value from either the left side, using values slightly smaller, or the right side, using values slightly larger.
Okay, one-sided limits. Got it.
Yeah,
So how do we know if a limit actually exists when we have these different approaches?
great question. A limit only exists if the function approaches the same value from both the left and the right.
Ah, so it's all about consistency. If the function has a clear target in mind, regardless of how s gets there, then the limit exists.
That's right. But if the left-hand limit and the right-hand limit disagree, then the overall limit at that point doesn't exist, which we often abbreviate as D&E. It's like trying to meet a friend at a park with multiple entrances. If you don't specify which one, you might end up in completely different spots.
I can definitely relate to that. Miscommunication strikes again. But what about those situations where a function just keeps growing larger and larger, or smaller and smaller, as it approaches a value? Does that mean the limit doesn't exist?
Excellent point. That brings us to the fascinating realm of infinity. In those cases, instead of approaching a specific numerical value, the function might be heading towards positive or negative infinity.
Okay, now we're talking. Infinity always makes things interesting. What would that look like for a function?
Picture a roller coaster climbing a hill that gets steeper and steeper. You can see where it's headed straight up.
Yeah, even though it never actually reaches the top, you know it's going to keep climbing higher and higher.
That's the idea. And in these cases, we often encounter something called a vertical asymptote.
Vertical asymptote. Now that sounds familiar. I vaguely remember that from my math days.
It's a line that the function gets infinitely close to but never actually touches, kind of like that roller coaster climbing forever.
Wow, limits can help us describe those extreme behaviors too. That's pretty powerful.